Hey everyone, let's do another example. This one's got something going on that's going to kind of make things interesting, I think. We've got a beam, but this beam's got a little attachment to it, this little L-shaped attachment. And there's 200 pounds being pulled down on this beam at the end of the attachment. We want to see how that affects things. And so here's the free body diagram for the entire system. And we could write out the equations real quick. Sum of the forces in the x. Of course, I only have the one, and that's a sub x, so that's going to just be 0, right? So that's gone. So I'm not even going to label that ax and ay. Well, I'll label it ax, but I'm just going to do a in the y direction is to make my life simpler. Sum of the forces in the y, I have a plus c, right? Because that's a roller, so it only has an upward force, minus 200 pounds, and that's equal to 0. So a plus c equals 200 pounds, no big deal there. And then sum of the moments, and we'll do the sum of the moments about A. And when we do that, nothing there, but then I have 200 pounds times 7 feet, right? Because that's down in this direction. That's going to be, it's pushing down, so it's trying to rotate it clockwise, so that's negative. And then C is trying to rotate it counterclockwise about A. And so that's going to be positive, so plus c, and that's times 9 feet. And that's all equal to 0. So when I solve this out, I get c is equal to 1,400 foot-pounds over 9 feet, which is just 1,400 over 9 pounds. And I just leave it in that format. So there's the force at C, and so I can figure out what the force is at A, because A plus C is equal to 200, right? And so A is equal to 200 pounds minus 1,400 over 9 pounds, which is what? This is 1,800 over 9, so that's going to be 400 over 9 pounds. Okay, just leaving it in fractional form. I don't have my calculator to calculate it out, but it doesn't matter, it's a number. Okay, but now we want to look at what's going on as we're looking at this thing. Now, if we make a cut between, and actually it's I better label this as E, and that's at 8 feet. Okay, but let's take a look at what's going on. Let me make a cut somewhere between A and E. And so when I do that, I've got the A force, which is the 400 over 9 pounds. And then I have the V, and then the moment about A. And so when I look at the sum of the forces in the Y, I get 400 over 9 pounds minus V is equal to 0. So V is just equal to 400 over 9 pounds. And then the sum of the moments about A, I've got minus V times X, because this is some arbitrary distance X, plus M is equal to 0. So that's just pretty simple. M is equal to 400 over 9 pounds times X, whatever X turns out to be. But the interesting question might be, well, wait a minute, what about when I'm in between here? Well, it turns out when I'm in between B and E, the answer doesn't change. And this goes back to the whole concept of, is it touching it, right? This 200 pounds is not touching up there, right? It's touching the bar at this location, not up here. So when I examine this bar, what I want to do is I'm going to put a line in there, and I'm going to say, hey, I've got this horizontal bar, and then I've got this L, and I'm going to treat them like two different things. And so when I look at the horizontal, or when I look at the L, I've got this 200 pounds in here, and then we need to remember that this acts like a fixed support, right? It acts like a fixed support, so it exerts forces in the X. We'll call that E sub X, E sub Y, and then it'll also exert a moment, M. I'm going to call that M sub E. And so when I do the sum of the forces in the X, clearly there is none. So that E sub x is equal to 0. But when I look at the sum of the forces in the y, I discover that E sub y is equal to 200 pounds. Now, let's go back to the whole idea of due to and acting on. This is 200 pounds, right? So E sub y is a normal force. Actually, it's really going to be a tension because they're trying to tear each other apart, but let's just leave it alone. Due to the horizontal bar acting on the L shape. And then there's going to be a moment, m sub e, and when I do the sum of the moments, I'll do them about this point right here. I'm going to have m sub e, and then this is trying to rotate things in a counterclockwise direction, so plus 200 pounds times 1 foot. Because keep in mind that distance from here to here is 1 foot, so when I bring up the line of action of the 200 pounds, I don't care about this diagonal. I bring up the line of action, this distance right here is 1 foot. So the lever arm, if you will, from E to the line of action of the 200 pounds is 1 foot, the perpendicular distance. And so m sub E equals minus 200 foot-pounds. Okay? Now, what's causing that? That's a moment acting on the L caused by the horizontal bar. So now when I do the force diagram for the horizontal bar, I'm going to have A sub y, or A. So what was that? 400 over 9 pounds. And then remember, E sub y, which is 200 pounds, it's a force due to the horizontal bar acting on the L shape, which means Newton's third law comes into play. So there's a force acting on the horizontal bar due to the L shape, but it's going to be equal and opposite. So that's going to be 200 pounds down. But where's that happen? That happens at the 8-foot mark, right? That's taking place with the fixed support, which is at the 8-foot mark. Here, this force doesn't exist here. It's not there. This force is over here at the 8-foot mark. Okay? I mean, it's down here, but when I consider just the horizontal bar, it's not there until we get to the 8-foot mark. All right, so let me just label this 8V. Then there's V, and there's that moment, right? So there's 200 pounds, and that's it. Oh, no. Then there is m sub e. So there's a moment now. Let me go back to purple. There's a moment of 200 foot-pounds, and m sub e is negative, right? M sub e is, it's clockwise. And so that's the moment caused by the horizontal bar acting on the L shape. So the moment caused by the L shape acting on the horizontal bar is going to be in the opposite direction. So if this is clockwise, then this moment exists right there. And so I'm just going to label that m sub e, and that's equal to 200 foot-pounds. And that's going to be counterclockwise because it's equal and opposite, right? Third law is really important here. It's super, super important. And so now I can take a look at what's going on at this location. Now, I'm going to assume that this location is between C and E. It's between C and E. Okay? So this force at C, right, the 1,400 over 9 pounds isn't there yet. It's not there yet. So that force isn't there yet. Okay, then, when I look at the sum of the forces in the Y, I've got 400 over 9 pounds minus 200 pounds minus V is equal to 0. And so V is equal to 200 pounds minus 400 over 9 pounds. Right? Whatever that turns out to be, we don't really care. I mean, we kind of care, but you can calculate that out. It's interesting is the sum of the moments about A, because I'm going to get 200 pounds times 8 feet, right? Because this is 8 feet right here from that pivot, and that's negative, minus v times x, because that's trying to rotate it, right? Then plus m. But here's where this is very different than it was in any of the previous problems. I've got this moment being applied at this location because of the shape of this thing. So there's a moment twisting this bar at this location, and I have to count that. So plus m sub e, but m sub e, going back to here, was, well, the magnitude of m sub e is 200 foot-pounds. And so that's got to be included, and then I set that equal to 0. And so I know what v is, that's just a number. This would be 1400 over 9 pounds, right? And then when I solve this now for the moment, I'm going to get Vx, which is 1400 over 9 pounds, times x, plus, because this becomes positive when I bring it to the other side of the equal sign, plus 1600 foot-pounds, and then let me actually add plus 200. Well, actually, that'll be minus because it's going to the other side. So 1600 minus 200, and that's going to give me 1400 foot-pounds. And so my moment is equal to the slope times x plus that constant. And so, again, you'll notice if I do the derivative of the moment, I get the shear force. All right, so this is just a quick problem that involves some situation where I put a moment in. Sometimes they'll put the moment in to just say, hey, this is being twisted at this location, but this kind of gives you an idea of how that twist might take place. The other interesting spot here, and I won't go into this, but you can work this out. If I go to the points between C and D, I get nothing. Okay? There's no shear force, there's no bending moment at this location. And if you work out the physics behind it, you'll do everything I've done except choose a location past the 9 feet, and you're going to see you get nothing. The M and V will both solve out to 0. So give that a try if you're really interested. Should be interested, but I'll let you decide on that. Okay, just an interesting problem here. Again, piecewise functions, if we're graphing, we'll have piecewise shear forces and piecewise bending moments. All right, you have any questions on this problem? It's a cool problem. But I want to emphasize, this is a fixed support in here. It's acting, does everything like a fixed support does. And then you do the do-tos and the acting-ons, and you find out what's going on with the horizontal member. You've got to apply Newton's third law, even for the moments. All right, have any questions, leave them in the comments below. Thank you.